welcome back. In the last lecture, we have seen in the situation when we cannot compute the integral, then we use trapezoidal method to approximate the integral. So, in this lecture, we are going to see another form of approximation. There in the trapezoidal rule, what we have seen is that we have joined the line f of x naught and f of x 1, f x 1, f x 2 like this with the partition P, and then what the resultant geometric figure what we got was trapezium. So, we computed the area of the trapezium and then that is what was the approximation for the integral, and then we have made some noise about the error we are committing. So, today we will see a different kind of approximation. Suppose we have let us say a function which is like this thing. So, then let us divide this into let us say 4 equal parts, x 0, x 1, x 2, x 3 and x 4. Now, what we want to do is that we would like to have a parabola passing through x naught, x 1 and x 3. We can have a parabola. Let us say we have this parabola. This is a parabola which is passing through x naught. This is f of x naught. This is x 1 f of x 1. This is x 2 f of x 2. And again we have here, so these 3 points. So, if we have another, we can have a parabola like this. So, as you can see, first we have gone from this is P 0, this point is P 1, P 2. Then next we are going to have P 2, P 3, P 4. So, similarly, if we make our partition to be even part, let us say a partition if we consider P to be x naught less than x 1 less than x 2, it goes like this to some 2 L x of 2 L even point. Then for each 3 points P 0, P 1, P 2 we have a parabola, P 2, P 3, P 4 we have a parabola. So, by taking small and small the norm of P, what we are going to get is that that this approximation is going to be a valid approximation for the integral. So, let us try to compute the area of this parabola between these 3 points. What is going to be the area? For convenience, let us say we take the point x naught to be minus of h. Remember that in the partition we are going to have the subintervals of equal length. So, now suppose we have a parabola something like this, which passes through, this is P 2, this is P 1, this point is P naught, that is x naught, f of x naught is our minus of h, this is x 2 and this is 0. So, this is okay. Now, the parabola is given in general by the equation parabola equation is ax square plus bx plus c. Now, if we want to find the area under this region, so what is the area? So, the area is going to be minus of h to h for this case, and then ax square plus bx plus c dx. Now, if we compute this, then this is going to be twice 0 to h ax square plus c dx, and this is equal to h by 3. You can compute that this is 2 a h square plus 6 c. This is what is the area what we have found. Now, look at this for this parabola. What is f of x naught? F of x naught is x naught here we are taking to be minus of h. Therefore, this f of x naught is going to be a minus of h square, that is h square minus of b h plus c, and f of x1 is equal to 0 here. This is our x1 is equal to 0 here. Now, 0 means this is equal to c. Now, f of x2, this is equal to x2 is h. So, this is a h square plus b h plus c. Now, you can see that f of x naught plus f of x2 is equal to 2 a h square plus 2 c. Now, so f of x naught plus 4 times f of x1 plus f of x2, this is going to be 2 a h square plus 6 c. So, this is precisely this area under the parabola. So, now getting the value only by knowing that f of x naught, f of x1 and f of x2, we are able to find the area of the region under this parabola. So, now I have a parabola with the equal distance. So, obviously, if I shift the parabola to any other position with the equal distance, that is also the formula is going to be true in that case. So, now this is precisely is what the Simpsons rule says. Suppose we have take any let us say P2, P3, P4. P2 is x2 f of x2 and P3 is x3 f of x3 and P4 is x4 f of x4. Now, area under this parabola passing through P2, P3 and P4, this is equal to h by 3. H is the distance between x2, x3 and x3, x4, h by 3 f of x2 plus 4 f of x3 plus f of x4, correct. So, now of course, now if I want to find a b f of x dx, this we are going to approximate. If I take n to be large, we can approximate this area to the area under the curve of f of x. So, this is equal to h by 3 f of x naught plus 4 f of x1 plus f of x2 plus this is between P0, P1 and P2. Now, P2, P3, P4 f of x2 plus 4 f of x5 x3 plus f of x4. Then again P4, P5, P6. In this case, we will go on like this. So, we go up to this. Now, we are considering for this as n is even, the partition n even. So, this is going to be, last term is going to be f of x n minus 2 plus 4 f of x n minus of 1 plus f of x n. So, writing this is h is what? H is basically b minus of a divided by n. So, this is 3 n, this is f of x naught plus 4 f of x 1 plus 2 f of x 2 plus 4 f of x 3 plus 2 f of x 4 goes like this, plus 2 f of x n minus of 2 plus 4 f of x n minus 1 plus here the last term is f of x n. So, this is what it is called the Simpsons rule. Remember that in the Simpsons rule, the partition what you are making, that has to be an even number. There are even partition. So, x naught, x 1, x 2, x 3 up to x 2 l, n has to be equal to 2 l for some l. And so, using this, so let us compute using the Simpsons rule. Let us compute the approximate integral for, let use Simpsons rule. With n is equal to 10 to approximate integral 0 to 1 e to the power x square dx. Now, here n is equal to 10. So, therefore, delta x, this we can say b minus of a by n, b is 1 here. So, 1 by 10 which is equal to 0.1. Okay. Then by Simpson's rule, integral 0 to 1 e to the power x square dx is approximate to 0.1 divided by 3, this is h by 3 what we have got. Now, this is f of 0 plus 4 times x 1 is what? F 1 h is 0.1, I am starting with x naught to be 0. So, x 1 is going to be 0.1. So, this is 0.1 plus 2 f of 0.2 and plus 4 f of 0.3 plus 4 f of 0.9 plus this is plus f of 1. That is what we are going to get. So, now if you do this, then this is plug in the value, what is your f? E to the power x square. So, first one is 1 and then the second one is 4 into e to the power 0.1 square and plus 2 into e 0.2 square, go on like this, plus 4 into e to the power 0.9 square plus e. So, approximately this what we can write it as 1.4 if you calculate with your calculator. So, what you are going to get is this. So, in Simpson, in trapezoidal rule, you are approximating through straight line, and in Simpsons rule you are approximating through parabola, and in Simpsons rule we need to take care that the partition what we are making the sub intervals that has to be even in number. So, that is how we are going to approximate each 3 points the parabola passing through it, and we got a nice approximation. So, as a matter of fact, just for the sake of knowledge and the completeness we are not going to prove, but I can give you the kind of tentative idea that what is the error we are going to make from the exact value of the integral. So, here we need to assume our f what we are integrating is fourth order differentiable, and this fourth order derivative of f we are assuming it to be continuous, and assume that mod of the fourth order derivative is less or equal to m. Then the error term in the Simpsons is equal to a to mod of a b, and this is the approximation, let us say the s, the approximation. This is going to be less or equal to, this is going to be less or equal to b minus of a to the power 5 divided by 180 to the power n to the power 4 into the bound of f 4. This is the error term for the Simpsons rule, and as we have said that in the trapezoidal rule what you need is the f double prime. You do not need to go to the f 4 to calculate the error like in the Simpsons test. Okay. So, this two method which helps us to compute approximate the integral whenever we get into trouble of calculating the integral precisely, then we have this two powerful tool to approximate. Okay. So, another interesting I mean useful thing to compute integral what we have seen in class in our high school is to substitute. Now, what is the substitution rule here in the definite integral? So, let g from a b to r be a differentiable function and g prime is continuous on a b and f is continuous on the range of g. Then we can talk of the composition of f and g, because f is defined on the range of g, therefore, f compose g is defined. So, we are defining that f compose g is well defined. So, we can talk of a to b f of g of x of g prime of x. Remember that here we are assuming g prime is continuous and f composed with g is continuous. So, this is a well defined object. Now, the substitution rule says that this is equal to f of y dy, and this integration will go from g of a to g of b. So, the proof is easy and also an application of fundamental theorem of calculus. So, as f is continuous on the range of g, which is in an range of g is going to be an of course an interval, because g is a continuous map from a b. So, definitely the range is going to be an interval. So, now by fundamental theorem of calculus 1, this f is going to have an antiderivative. Let us say f is a map from C to D, then capital F of x from C to x f t dt if we define, then this is going to be an antiderivative of small f. So, let f be antiderivative of f. Now, you consider this f composed with g, because the range of f, the domain is of this capital F is nothing but the domain of small f. Therefore, f composed with g is defined, because small f is defined on the range of g. Now, g is a differentiable function, capital F is a differentiable function. Therefore, f composed with g is also a differentiable function. Now, if we take the prime of this, then by chain rule we know that this is f prime of g x into g prime of x. Now, what is our capital F? Capital F is nothing but the antiderivative of small f. So, therefore, this is equal to f of g x g prime of x, and that is precisely what is on the left hand side of the statement. Let us say call this as star. So, therefore, by the fundamental theorem, and this is a continuous function, and so by fundamental theorem of calculus, what we are going to get is that we are getting by calculus 2 integral a to b f of g of x g prime of x dx. Remember that we are taking here to prove that f is a nice function such that capital F composed with g prime is continuous. That is one of the condition we have imposed on fundamental theorem of calculus. So, if we choose our f to be a nice function, so this is this is f composed with g is a continuous function, g prime of x is a continuous function, the way we have imposed the condition on f and g. That is where we are giving that g prime is continuous. So, then this is equal to, by fundamental theorem of calculus, is nothing but f composed with g at b minus f composed with g at a. So, this is precisely equal to f composed with g at b. So, this is equal to some, let us say f is an antiderivative of f what we are taking. So, f of x is equal to some c to x f t dt. Then this is c to g of b minus c to g of a. So, this is going to be equal to integral of g of a to g of b f t this is f of y dy, because that is what is the capital F is. So, this substitution is very very important, and which we have familiarity while we are in our class in high school, but nevertheless let us just take one example. Now, evaluate integral 0 to 4 square root of 2 x plus 1 dx. Now, what is so if I take my y to be 2 x plus 1, then obviously now this is going to be equal to, at 0 this is 1 g of this, and then this is going to be 9, and then this is equal to square root of 2 x, this is square root of y dy, and then this dx is g prime of x, this is g x, g prime of x is going to be equal to 2. So, then this is 1 by 2, if I do, then this is dy. And so, we know very easily how to compute this. Now, if you compute, this is what you are going to get to be 26 upon 3. Okay. So, now let us see that when we are talking about the fundamental theorem of calculus, suppose I have a g x which is equal to a to g x f t dt, and here is g is differentiable, small g is differentiable, and f continuous given to us. Instead of x, I have a to g x. Now, if I define f of x to be integral over a to x f t dt. Now, f being continuous, this capital F is also differentiable by fundamental theorem of calculus. So, g is equal to f composed with f of g of x, g of x. So, this is nothing but f composed with g at x. Therefore, g prime of x, when we are going to compute this, then this is going to be f prime of g of x into g prime of x by chain rule. So, this is, for example, if I want to compute 0 to square root of x cos t dt, this is my capital G. Therefore, let us say this is our g of x. Then g prime of x, this is equal to, so here what we are taking, that f of x equal to cos t. Therefore, f prime, this is at g x, f is cos square root of x, and g prime of x, little g x is square root of x, 1 by 2 square root of x. So, this is precisely what you can compute. So, whenever you have 0 to g of x, then this is f compose antiderivative of this. So, g prime of x is essentially this. So, this also helps you to compute various integral, even though if you do not have from a to x, but remember, if a to g x, all the time you need to check that this small g has to be differentiable. That care you need to take. Okay. So, this is fine for today. So, what we are going to discuss in the next lecture is that how to find the area between region basically enclosed by two curves. So, that is what will be our next topic of discussion. So, thank you very much.